All right, we will begin talking about Chapter 6, which is titled Exponential and Logarithmic Functions. And let's share our goals. We want to be able to determine the multiplier for exponential growth and decay, and write and evaluate exponential expressions to model growth and decay situations. So first of all, let's talk about what that growth and decay situation is. We know when something grows, it's getting larger, and it decays, it's usually diminishing, decreasing. Exponential growth and decay needs to model one of the following equations. Notice, n equals c times 1 plus r to the power of t. R is your rate of growth or decay. C is usually that constant value you're starting with. T is time, and n is going to be that value, obviously, when you finish over that period of time. So if it is growing, it has to be a number bigger than 1. So notice in our parentheses here, we would have, if we added a value to r, and let's say it's growing by 3%, then 3% would go in as 0.03 for r, and we would have 1 plus 0.03, so we're looking at a number greater than 1 in that parenthesis. The same thing would hold true in decay. If you say, hey, our profits are decaying by 3% per year, then you would have 1 minus your 3%. Remember, 3% is going in as a decimal equivalent. And from there, that's like saying 1 whole take away 0.03, or 100% take away 3% is 97%, but then that turns into a 0.97. So your result is that you end up with a number less than 1, so it would end up being a decay situation, and up here again the number would have been a number greater than 1 in the parenthesis. So anytime you're multiplying by 1, nothing's changing. When you're multiplying by bigger than 1, it's going to grow, and by less than 1, it's going to decrease. So those are our two basic setups. Those are the two equations we'd like you to be using. So now, if we give you a real-life investment problem, suppose you've invested $1,000 in the company's stocks at the end of 1999, and that the value of the stock increased at a rate of about 15% per year. Predict the value of stock to the nearest cent at the end of the years 2004 and 2009. So again, you're thinking, n equals, using that prediction, this one told us that we invested and the value of the stock increased, so we know it's adding, and to the power of t. So now look at that. There are some other values you should be able to put in there, and that's what you need to do to calculate your first one. So go ahead and do that. Put your other values in that you were given, and the question is, did they give you n, did they give you c, did they give you t? And I believe at the question there's two different years, so don't do them at the same time, obviously. So calculating quickly with the help of a calculator if you need it, we're looking at the first situation for the year 2004 being n times, or n equals 1,000 times 1 plus the 0.15 to the power of 5. Why is it 5? Because from the year 1999 to the end of the year of 2004, that's a period of 5 years. The 1,000 was the starting amount that you invested, so that should have gone in for C. So you would do the same exact thing for 2009 with one exception. You would have to change your year time factor. And so you're looking at, so look at that. Over 5 years, we have more than doubled our money with that 15% increase. So if you were investing, you're getting a pretty good return. And this was only after 5 years. But 15% is a very good rate in our current situation right now. You're not going to see that probably unless you're heavy into some investment opportunities. So next choice would be, obviously, we could do a decay. But let's talk about a decade growth factor. Decade, we know, is obviously a period of 10 years. So if a population's growth rate is 1% per year, what is the population's growth rate per decade? We're still thinking about that growth and decay formula that we used in the beginning there. So I don't give you a value here, so you can't go off of that, but we know it's at 1% per year, and we know it's going to be sitting there for a decade. So if you would use the part of the equation that involves that calculation with time and rate, you should be able to come up with something. So try it. Do a quick calculation. What is the population's growth rate per decade is what we're looking at. So if you're thinking about something like, hey, I've got that 1 plus that 1% per year, so 1.01, for a decade is 10 years, you are then getting a fairly long, not large, but long decimal here. But then you have to go back and say, well, wait a minute, take off that original amount that I would have invested, which, again, we didn't have a value on this one, but that would give you the 0.104622123 decimal. So then you have to be able to assume, because we know decimals get turned 2% by moving 2 places to the right, that we're looking at about a 10.5% growth factor if it was for the decade. So that's a little better than the 1% we were talking about per year. So don't just assume it's 1% per year, so 1 times 10 is 10%. If you actually do the number crunching with the extra pennies there, you're getting a little better bang for your buck. All right, next topic, and that is it actually. So let's go back and just look at some just growth and decay combinations, and if you have any questions on either of those, bring that to class with you, and we'd be glad to answer some questions for you.